Minerals are characterized by certain definite physical properties, chemical composition, optical properties and internal molecular structure, and hence the study of minerals is made under different heads like physical mineralogy, chemical mineralogy, optical mineralogy and X-ray mineralogy. The optical properties such as refractive index, twinkling, birefringence are important for the identification of minerals individually and also when they are the constituents of the rock. Optical mineralogy deals with the study of optical properties of minerals in thin sections and grains under special type of microscope called petrological microscope, which differs from an ordinary biological microscope in having a set of additional fittings. A biological microscope makes use of ordinary light which travels with rapid forward and backward movements called vibrations, taking place regularly in different directions. Such an ordinary light is not suitable for the determination of optical properties. Light suitable for the determination of optical properties should have its vibrations taking place in one definite plane. Such a light is called polarized light. Therefore, ordinary light has to be converted into polarized light before it can be used for the determination of optical properties. A fitting to a microscope that can convert ordinary light into polarized light is called the polarizing prism, and petrological microscope is fitted with two such polarizing prisms and thus differs from an ordinary biological microscope which does not have any such fittings. Therefore, a petrological microscope is often called a polarizing microscope. Petrological microscope is a type of microscope used in the study of thin section of minerals and rocks. It differs essentially from an ordinary biological microscope in having a revolving and graduated stage and two Nicol prisms, one below the stage and the other above it. Nicol prisms serve the purpose of converting ordinary light into polarized light suitable for the determination of optical properties of minerals. A petrological microscope is therefore called a polarizing microscope. There are several makes of petrological microscopes. The normal petrological microscope consists essentially of a light source or mirror, a substage condenser, a revolving and graduated stage, a tube called microscope tube, an objective, an eyepiece and two Nicol prisms, one below the stage and the other above it. The microscope stage, in its simplest form, it is a circular disc with an opening in the center through which the light passes. The thin section of a mineral or rock is held in place on the microscope stage usually by the spring clips. It is rotatable and is graduated in degrees with a vernier attached to it. The amount of rotation of the stage can be read off directly from the graduations marked on the stage, aided by the vernier. A small knob is provided at the rim of the stage and it allows the stage to be clamped in any position. The sub-stage apparatus, this is below the revolving stage and consists of the lower Nicol or polarizer, an iris diaphragm and a condenser. The sub-stage apparatus can normally be swung out of the light path or be completely removed by lowering it to its minimum position. The condenser, it consists of two simple lens elements and its functions is to supply a cone of light just large enough to fill the front lens of the objective completely, giving maximum illumination. Iris diaphragm, it consists of a number of overlapping leaves or membranes attached by pins to the rim of a casing and having a central opening which is enlarged or diminished by moving a lever and is placed above or below the polarizer. The polarizer, it is a Nicol prism mounted in a circular metal case forming the bottom unit of the substage assembly and is also called as a lower Nicol. The polarizer can be rotated through 360 degrees and can easily be slipped from its mount or swung from the light path. Ordinary light that is reflected by the mirror on entering the polarizer is converted into polarized light with vibrations confined to the shorter diagonal of the rhomboidal face of the polarizer, vibration plane of the Nicol. In most microscopes, the vibration plane of the polarizer coincides with the vertical cross wire seen in the field of view when we look through the microscope tube. But in some microscopes, the orientation of the polarizer is such that its vibration plane coincides with the horizontal cross wire seen in the field of view. Hence, it is essential to know the definite orientation of the polarizer in a microscope before it is used. The microscope tube in its simplest form, the microscope tube is a straight metal tube that separates the objective and the ocular. In most microscopes it is straight, but in some microscopes it is inclined at an angle to enable the observer to sit comfortably and work. The ocular for eyepiece, the removable lens assembly that fits into the top of the microscope is the ocular or eyepiece. It magnifies the image produced by the objective and increases the field of view. The ocular used at low to medium magnifications consists of two simple plano-convex lenses of different focal lengths, the focal length of one being 1/3 of the other, and are separated from each other with their plane surfaces towards the eye and by a distance equal to the sum of their focal lengths. The small upper lens nearer to the eye is called the field or collective lens. Two thin and delicate wires are placed at the focal plane of the ocular in the north, south and east, west directions and are attached to a sliding sleeve within the microscope tube. The vibration planes of the two polarizing prisms, polarizer and analyzer of a microscope are oriented to the cross wires in the ocular with either the vibration plane of the polarizer or of the analyzer coinciding with the vertical or horizontal cross wire. The magnification of the ocular is usually marked on the metal case of the ocular and ranges from about 2x to 16x. The objective, it is the crucial component of any microscope which acts with the ocular to perform two basic functions of the microscope: magnification and resolution. It is also called the object lens since it is nearer the object under examination and is the one that first receives the light from the object itself. It brings the light to a focus in the principal plane of the ocular, producing a real and magnified image. Magnification is the first principal function of the objective. The magnifying power of an objective is called its initial magnification. The magnification is usually marked on the metal surface and ranges from 1x to 100x. Objectives may be classified according to their magnification into low, medium and high power. Low power objective is used for observing large scale features such as rock texture, and medium power objective is used for general observation, while high power objective is used for observing small scale features and interference figures. Resolving power is the second function of an objective. Quantitatively, the resolving power of the objective is its ability to reveal the fine details Mounting of the objectives. Objectives are mounted on the microscope tube in various ways. Each petrological microscope is designed in such a way that objectives may be changed simply and quickly. In old types of microscopes, each objective is screwed into place as it is needed. Modern types of microscopes are provided with their revolving nose piece system or objective clutch system for mounting the objective. Usually, the microscopes with inclined tubes have a multiple lens nose piece that allows objectives to be interchanged simply by rotating the nose piece. In vertical tube microscopes, the objectives normally screw into the centering ring or collar, held against the microscope tube by a spring clutch arm. For accurate work, the objective should be centered. Centering means making the center of rotation of the stage to coincide with the axis of the microscope, which is the intersection of the cross wires. Two screws are provided in the objective collar for centering the objective, and these are called centering screws. The working distance. The working distance of an objective is the distance between its front lens and top of the cover glass of the micro slide when the object is in focus. For low power of medium power objectives, it may be several centimeters, but for high power objective, it is a fraction of a millimeter. Hence, great care should be taken while focusing under high power objectives, since over focusing results in the breaking of the cover glass of the microslide or in scratching the lens of the objective. The Bertrand lens. It is simple lens which simultaneously with the ocular serves to magnify the interference figure, bringing the image of the figure into focus in the ocular. It is usually inserted in a slot provided in the upper part of the microscope tube above the analyzer and can be drawn into when its use is necessary or out of the slot when its use is not necessary. The analyzer. It is a Nicol prism like the polarizer, but is mounted in the microscope tube above the objective and below the Bertrand lens so that it can be slid into or out of the position. Since it is mounted in the upper part of the microscope above the microscope stage, it is also called upper Nicol. Its function is to produce phenomenon of light called interference, resulting in the interference colors. Its vibration plane is usually either vertical or horizontal in the field of view, coinciding with either the vertical or horizontal cross wire like the polarizer. It is usually fixed in a microscope with its vibration plane at right angles to the vibration plane of the polarizer. This position is also called Nicol's position. The focusing adjustment. The frame of the microscope consists of an arm and a base. In vertical tube microscopes, the arm is normally connected to the base by an inclination joint that allows both tube and stage to be inclined. The focusing adjustment is incorporated in the microscope arm. In straight tube microscopes, a large knob or the upper part of the arm is used for coarse focusing and a smaller one for fine focusing. Generally, focusing is done by raising or lowering the microscope tube with its optical parts attached. Coarse adjustment is effected by a rack and pinion by operating the large knob, while the fine adjustment is effected by operating the smaller knob. In the recent types of microscopes with inclined tubes, there is a single knob on the lower part of the microscope arm with coaxial coarse and fine adjustments, and by operating this knob, The microscope stage is raised or lowered rather than adjusting a microscope tube. Coarse adjustment is effected for focusing under either low power or medium power objectives, while fine adjustment is effected only for focusing under high power objectives. Refractive index of a crystal is the sine of the angle of incidence divided by sine of the angle of refraction. However, only glass and crystals in isometric system are singly refractive, while all minerals belonging to tetragonal, trigonal, hexagonal, orthorhombic, monoclinic and triclinic systems have two refractive indices. Refractive index indices Ri of each mineral is unique. There of course are overlaps in ranges, but still determination of Ri along with other tests can help in mineral identification. The refractive index of a mineral is determined by refractometer. The instrument is designed optically to use the phenomena of critical angle, that is total internal reflection, to provide direct refractive index reading and is also known as critical angle refractometer. However, the principle can only be used if the Ri of the mineral being tested is less than the refractometer's lead glass prism, which has an Ri of 1.86. If the mineral Ri is greater than the Ri of this prism, the ray will be refracted out and there will be no total internal reflection. The mineral is placed on this glass prism in such a way that one of its flat facets is in good contact of the prism. In reality, however, a contact fluid, saturated solution of sulfur in diiodomethane and tetraiodethylene with refractive index equal to 1.81 is used to ensure good optical contact between the gem and the lead glass prism. The principle of total internal reflection occurs as follows. 1. As light converge from the prism onto the surface of the mineral, ray L1 and L2, which have larger angle of incidence compared to the critical angle, are reflected back into the denser prism following the laws of total internal reflection. Rays L4 and L5, whose angle of incidence is less than the critical angle, are refracted into the gem, but ray L3, which is incident just at the critical angle, travels along the interface of the two mediums. Thus, when light rays passes from a dense medium to a rarer medium of gemstone, the light rays will be reflected back from the surface of the gemstone over an arc of incident angle greater than that of the critical angle of incidence. This critical angle is determined by the Ri's of both the denser medium and the gemstone. The dense medium in the refractometer is a glass prism of known refractive index. The critical angle gives the direct measure Ri of mineral as follows. Refractive index of rarer medium mineral sine of critical angle is equal to refractive index of dense medium prism of refractometer, that is, and refractive index of mineral is equal to sine of critical angle multiplied by the refractive index of the refractometer prism. Refractive index of mineral is equal to sine of critical angle multiplied by the refractive index of the refractometer. Let us now look at the figure. The basic construction of the critical angle refractometer is shown in the figure. Here, the light rays arriving at the interface between the mineral and the glass prism and having an angle of incidence less than the critical angle ION are not reflected into the lens system. However, those rays having an angle of incidence greater than the critical angle are reflected into the lenses and illuminate a scale graduated in Ri values. The image of the scale is inverted by a mirror and then focused by the eyepiece. The end result is viewed as a dark top section and as an illuminated lower part. The horizontal shadow edge between the two parts is the measurement of the refractive index of the mineral. In anisotropic minerals, the index of refraction differs with direction. A mineral fragment showing high relief in one direction and low relief in another is said to have variable relief, and such a mineral shows on rapid rotation of the microscope stage under plain polarized light without using the analyzer. Variation in relief with alteration of strongly marked and slightly marked borders giving a twinkling effect, and hence this phenomenon is called twinkling. Calcite is a very good example of a mineral showing twinkling. In calcite, the refractive index for the ordinary ray is 1.66. For the extraordinary ray is 1.49, and the refractive index of Canada balsam is 1.54. The refractive index 1.66 for ordinary ray is very much higher than that of balsam, while that 1.49 for the extraordinary ray is lower than that of balsam. Therefore, the rotation of the microscope stage brings about a strong change from high positive relief to low relief, which may be positive or negative, resulting in the alteration of strongly marked and slightly marked borders, twinkling. The difference between the two refractive index values is known as the birefringence. This is best seen in doubly refracting minerals like calcite, where refractive index is C-axis direction is 1.4864. Sigma light vibration in this direction is known as the extraordinary ray or E ray, and in the direction of A axis refractive index is 1.6585 mu. Light vibrating in this direction is known as ordinary ray or zero ray. It is also expressed as n raised to the power 2 minus n raised to the power 1, wherein n raised to the power 2 and n raised to the power 1 stand for the values of maximum and minimum refractive indices respectively in the crystal. The difference in Ri is also abbreviated as Dr, that is double refraction, or sigma. The difference in value between the maximum and minimum refractive index, that is sigma and mu, is tetragonal and hexagonal crystals. When faceted stones characterized by strong birefringence, for example peridot, zircon and sphene, are viewed from the table facet, the cult and back facet appears in two sets, doubling of the back facets. A 10x loop is quite handy to observe the doubling effect. If the table is cut perpendicular to the optic axis, the stone has to be tilted to notice the doubling effect. The doubling effect, however, is not obvious in the stones having weaker birefringence, for example apatite. The petrological microscope is a basic lab tool for a geologist which assists in identifying the optical properties of the individual minerals or the minerals present in the rock. Refractive index is an important optical property which helps in the identification of ordinary minerals and gem minerals using a refractometer. In fact, the minerals which possess a similar certain other optical or physical properties can be distinguished with the help of a refractive index. The property of twinkling is useful in identifying some of the antisporic minerals in order to identify doubly refracting minerals, the optical property birefringence plays a significant role. Thus, petrological microscope, the properties depending on light such as refractive index, twinkling and birefringence are unavoidable tools for the identification of minerals and minerals present in rocks.